Hello, everybody. Welcome, and thank you for joining today. Today, we're going to talk about Elasticsearch and aggregating, analyzing, and visualizing your logs with Elasticsearch in AWS. And within AWS, the standard thing that people do for log aggregation in the open source world is to use a stack that's called the ELK stack. And this includes three different pieces of software. The first of those is Elasticsearch for storing and analyzing the logs. But in addition to that, we have L for Logstash. Logstash moves data from point A to point B and is a very capable piece of software that can transform and deliver your log data to Elasticsearch in JSON format like it requires. Final piece of software there is the K is Kibana. Kibana is a thin web client that lets you visualize the data that's in your logs. On AWS, we have various technologies, streaming technologies that let you bring your data from point A to point B as well. And so today we're going to talk about EKK, which is an acronym which I don't love, but hey, Elasticsearch, Kinesis, and Kibana. And the idea here will be to flow your data through Amazon Kinesis Data Firehose, which collects and transforms that data, and then deliver to Amazon Elasticsearch service and visualize with Kibana as you would normally do. So for those of you that are not familiar with Elasticsearch, and that's vanishingly small because Elasticsearch itself is a tremendously popular piece of software. We've talked about the ELK stack, and really the log analytics workload and use case has driven a ton of adoption and popularity for Elasticsearch in the last, say, 5 or 6 years. Elasticsearch itself is a distributed system that allows you to rapidly flow data into it and perform analytics. It's based on the Apache Lucene engine at its core that supports not only searching your data, but also building aggregations on the numeric and other data in there. It's easy to get up and running, it's easy to get your data in, and it's easy to build visualizations with Kibana. All of that has really been driving a ton of popularity for Elasticsearch, as we said. You can see here from DB Engines, as of, I believe this is April of 2019, Elasticsearch sitting number 8 overall on the rank of database engines. And just to highlight the point a little bit, we see the growth of machine-generated data even far outstripping the growth of business data. So in a number of different areas, where we have, for one thing, in IT and DevOps, we have your engineers are building their applications, they're building their logs, and they're flowing those to monitor their performance, to find bugs, to find issues, and correct them. We see it very commonly. Customers are using Elasticsearch to monitor their infrastructure, so that if you're running, thousands of servers for your web application, you want to make sure everything's up and running, and that your CPUs are good, and that your network is good, and your disks are good, all of that. So all of those workloads and use cases generates tons of logging data. We also see, IoT starting to explode. We see mobile and gaming as big sources of application usage, and where application usage is, there are the logs. So those logs are also growing. And then finally, even as you architect and build in the cloud, all of the different components and services that you're using are generating logs themselves. So all of that log data is a huge amount of data, and there's a lot of good information in those logs, but it can be very hard to dig that information out and to get the insights you need. Elasticsearch, just how it works, it is a database technology, so it works like other databases in a lot of ways. So on the one hand, we have our log data on our servers or applications or networking, other logs, and that can flow into Elasticsearch. Elasticsearch is also a search engine, which provides relevant, fast search across document sets, things like your products if you're running an e-commerce site, or your data lake content if you're running a data lake. So, that data also can flow into Elasticsearch. And the native format there is JSON. So Elasticsearch is a REST-based application. You format your data and your queries as JSON. They go in. Elasticsearch builds an index across each of the fields that are in your JSON. So Elasticsearch as a search engine provides you search across fielded data that's formatted sort of lightly as JSON. And all of the fields are searchable. Queries come in on the other end. So for those of you that are not familiar with Kinesis Data Firehose, Firehose allows you to stream your data from point A to point B in a scalable and reliable way. With web scale data, and we have some examples here of, high scale data that's being created, you need a large pipe to move that data to where you want to send it. So Firehose provides you a serverless, scalable, resilient streaming solution that can get your web scale data from point A to point B. It's simple to set up. It deals with errors. It deals with backoffs. It deals with the challenges that you have in moving your data. So when we look at Firehose, Firehose has a number of integrations on the input side that make it easy to get your data into the Firehose itself. We have the Kinesis agent, which is a lightweight log shipper. It sits on your nodes and can tail your log files and ship them off to Firehose. Kinesis data streams, CloudWatch logs, CloudWatch events, and IoT also can deliver to Firehose. So one of the values that Firehose provides is a call out to a Lambda function that you define that is called for every record in the Firehose stream. And in the context of Elasticsearch, which requires a JSON formatted data document that you send into it, you can use this Lambda to transform your log lines into the JSON that Elasticsearch requires. And then on the other end, Firehose delivers directly to either S3, RDS, Elasticsearch Service, or Splunk. And we'll get into more detail, but again, this is a delivery that has backoff and retries and buffering and error handling. So it is a reliable way to get data into Elasticsearch Service. And as we think about it, Firehose, we would compare with the equivalent of Logstash. In the X stack, it'll be Firehose. In the ELK stack, it'll be Logstash. So just looking at those two side by side a little bit, the first is that Firehose is serverless. So you set up the Firehose and you push your data into it, but you don't have to manage any hardware or software or anything like that. It's just a REST API or, again, delivery directly from your other services. With Logstash, you run Logstash on a server of its own, and you have to set that server up and deploy Logstash to it and monitor and make sure that that server is up and running. Firehose scales elastically and automatically. So as you push more and more data into the Firehose, Firehose will expand to accommodate that data. With Logstash, the scaling story is a little bit more complex. You can scale up to the, vertically up to the maximum instance size, but once you get beyond that, you have to employ some kind of queuing mechanism. SQS is a common queuing mechanism that people use. And Logstash, then you have to auto scale across a set of instances. So the scaling for Logstash is less straightforward than Firehose, which just scales automatically. With Firehose, you transform your data with Lambda. With Logstash, it has a built-in set of transforms that include regexes and other control flow logic. Logstash can be a little bit easier on the transform. On the other hand, with Firehose and with that Lambda, you have a very generic mechanism that potentially lets you call out to other services to enrich your data with other metadata, and that can make it more attractive. Firehose itself will handle buffering the data. It handles errors in delivery. It handles errors in transformations with a built-in dead letter queue that goes to S3, so that when records fail to go through the pipeline, you have a record of that, and you can retry on those records. Logstash has a local buffering mechanism, and it does have some back off and retry as well. And then finally, Firehose does allow you to deliver your data to S3 in parallel with delivering it to Elasticsearch service. And we'll see in a second, that can be a very valuable addition because having your data in S3 allows you to maintain the long tail of all of the data that you're collecting at a lower cost point. So we're going to examine sort of the overall log analytics flow and talk through these pieces and how you use them. At a high level, you're going to have some set of data producers. These are generating logs, and these are typically servers, but they could be your application. They could be just about anything. You need to go through a collection phase where multiple writers don't all go to the same Elasticsearch cluster because the concurrency there will kill the cluster. So you need to collect those multiple streams of data and buffer them down into a single stream of data. And then you need to transform, as we said, Elasticsearch needs JSON. So your log lines are usually strings. And so you'll need to transform from your log lines to JSON. And then we deliver to Elasticsearch service. Now, the second pathway here is the one that I talked about for longer tail data and for historical data. As you're collecting your data, it's nice to ship that off to S3. Once it's living in S3 for permanent cold store, you can employ other tools like Athena, Redshift Spectrum, EMR, and even Elasticsearch service to analyze that data over a much longer time frame than you would use for your log analytics pipeline, which tends to be hot data. So let's start by looking at the producer side. And as I mentioned, we have a couple of options in terms of things that you put on the host. The first of those is Kinesis Agent. Kinesis Agent is very simple download to set up. It's about a 10-line config file. You just point it at your log and you point it at your Firehose data stream, and away it goes. At a more complex level, you can use the Kinesis producer library. That is a piece of Java code that you specialize. So if you have more complicated things that you want to do on the host before you ship the data off, KPL could be a good option for you. I generally would lean more towards Kinesis Agent. That again is a lightweight way to ship your data off of your servers. So let's talk about the collection phase. So when you set up a Kinesis data Firehose, you specify a number of different parameters. Amongst those, and sort of the most important ones of those, are your buffer size and your buffer interval. Your buffer size and your buffer interval are how much data the Firehose holds before it sends one record out. And you have to manage this a little bit carefully. If you set the buffer size at the smallest, and you set the time interval at the smallest, then you can have Firehose triggering quite frequently and sending out more connections or more messages than your cluster can handle. So you want to set this in the 5 to 10 megabyte range. That is a best practice anyway in terms of Elasticsearch for the size of the batch records that Elasticsearch receives and their processing. There's not a single number here. This is workload dependent. So you'll want to set it and tune it and play with it. And you're really trading off the flush timeout and the buffer size against the number of connections that you're making. If I'm sending 100 megabytes a second through, and I put my buffer at 5 megabytes, I'll have 20 connections in that 1 second. So then I have to be aware of that downstream. Elasticsearch has to be scaled to handle all of the connections that I'm making. If I'm connecting more than one Firehose to the same Elasticsearch service domain, that's going to really drive it a lot harder, because now not only do I have concurrency in terms of how many connections I'm making, but I'm building more of a multi-tenant solution where potentially I'm writing to 2 different indexes, and that drives usage of Elasticsearch harder. So let's have a look at transformation. And I talked through this, but the architecture of Firehose looks like this. I have my data source and my source records coming into my Firehose delivery stream. I have the Lambda transform function called for each of those records. And then I have my transformed records, which are delivered to Elasticsearch service. Now, by the side, I have possibly a failure for delivery, in which case the Firehose will write to S3. I possibly have a failure in transformation, in which case Firehose writes to S3. And I optionally can send all of my source records into S3. When we look at the transformation that Firehose does, Firehose will buffer up to 3 megabytes of data before transformation. So there's the buffer we already talked about, that's the delivery buffer. This is the transformation buffer. When it's full, it invokes the Lambda, and it passes the array of records that need to be processed. The Lambda function should process those records and then return with a status for each record. The transformed records go to the destination, right? And you can see on the left there, that is the records coming in. And on the right side, that is the message that I'm sending back. And I have a couple of different options here. I have OK and fail, and I have drop as well. So if you need to, you can use that Lambda pretty easily to filter the set of data that you're sending. And to make the point, this is an example of an Apache weblog line. As I said, all of your weblog lines will be strings. They'll look something like this. For Apache weblog, they'll look like this. And really what Elasticsearch needs to have is a piece of JSON that splits out each of the components of your log line and makes them available as JSON fields. So in this case, we have a verb, which is get. We have the bytes out, which is 6245. We have a timestamp, a request, host, et cetera, et cetera. How you structure this JSON is going to control how you're able to search and analyze your data in Elasticsearch. So this is an important step. If I want to be able to search for the verb in an HTTP request, then I need to split that out and make that its own field. Now, we do have several pre-built Lambda functions. As you're creating your Firehose stream, you can enable transformations, and then you have the option to choose one of our blueprints. We have a couple that are relevant for Elasticsearch. We do have native sort of transform code for weblogs and syslogs. This Lambda function is created in your account. You can go in there and modify it. You'll see also one of the blueprints is just general Firehose processing. That's just basically a framework that lets you insert whatever kind of processing you want. Okay, so let's talk about Elasticsearch service and what you do with it once your data gets there. So Elasticsearch service we came out with in 2015, with the idea that you should be able to use Elasticsearch as you're using Elasticsearch now. It supports all of the tools and APIs that you're used to calling. But at the same time, we take care of owning and operating the infrastructure that's running your Elasticsearch cluster. It's a managed service. It makes it easy to deploy and scale Elasticsearch in the AWS cloud. When you use Amazon Elasticsearch service, you deploy what we call a domain. The domain, as you can see at the core here, wraps a set of hardware and of course software that's running Elasticsearch. The service itself owns and operates a VPC so that the instances in your domain are within that VPC. We have 2 kinds of instances. We have data instances that hold data, respond to requests. So when you send queries or updates to Elasticsearch, those are all handled on the data nodes. You'll specify a data node count and an instance type when you create this domain. That is one of your knobs for tuning. We also have master nodes. Master nodes are orchestrators, so they do not respond directly to requests, but they do hold the cluster state in terms of the number of indexes, the kinds of schema that you have, the instances that are in the cluster, the location of all of the sharded data that you have in there. Those master nodes do provide a good deal more stability, and we do recommend that you use them for production settings. We have a load balancer in front of the cluster, so when requests come in, they're load balanced across the data nodes. And then we publish an endpoint via Route 53, which exposes the cluster for you to use the regular Elasticsearch APIs that you would normally use to send to Elasticsearch. We use IAM as our most core authorization and access control mechanism. You write policies that specify which users or principals have access to which data in the cluster. As of now, we have down to an index level in terms of granularity for API calls. We also have more sort of security layers that we'll get to in a minute. We do have some integrations with other AWS services. So you can see we send data to CloudWatch and CloudTrail. We send metric data to CloudWatch. This allows you to monitor what the cluster is doing and monitor the performance and ensure that you have enough resources online to handle your workload. With CloudTrail, we send audit data about who modified the cluster, who created the cluster, those kinds of things. On the input side, we have Kinesis Data Firehose that we're talking about today. We also have database migration service, which can migrate your data to Elasticsearch. And we also have integration with CloudWatch logs that can deliver data to Elasticsearch via Lambda. On the left, we have the set of tools that allow you to create these domains. We have command line tools, SDKs, console, CloudFormation, so you can maintain your infrastructure as code. When data comes into Elasticsearch, it's stored in an index. An index is a global structure for one set of data, right? When you use Firehose, you're going to specify the index that you want it to deliver it to, and optionally, you're going to specify a period over which that data is going to go into the index. The normal thing to do with a log analytics use case is to roll your indexes over daily, and so that today's index will contain all of the data from today, yesterday's index will contain all of the data from yesterday, etc. 5 shards is the standard sharding. That's the default shards that you get. When your data comes in, it will be hashed across those 5 shards. Those shards both store the data and operate on the data. So the shard is really the core component of scale within Elasticsearch. Elasticsearch is going to eventually map those shards onto instances in your cluster, and that's how the compute is put against and storage is put against your data. So you have a set of shards that holds all of your data. Those are your primary shards. Once you define that for an index, you can't change it. You can have dynamically a set of replicas. So replica is just a copy of the primaries. We always recommend that you have one replica. That is the default for Elasticsearch as well. That replica provides redundancy for the data in your cluster. Replicas and primaries are always put onto different instances in the cluster. So, as I said, Elasticsearch will distribute all of the shards to the data nodes in the cluster, and it does so in such a way that primary and replica go on to different nodes. When queries and updates come into the cluster, they are distributed across the shards that relate to those queries and updates. If I send a query that queries just today, then it will hit one shard from each of the five shards that I have. Could be a primary replica, but it will be one of each. If I send an update, it will go to the primaries. The primaries will write that update and then send it to any replicas. So as I mentioned, when you use Firehose, you can specify a rollover timing. You first of all, give Firehose a root string like logs, and then you're going to rotate either hourly, daily, monthly. The usual workload, we would rotate daily. If it's very high volume, you can sometimes come down to hourly. If it's very low volume, you can go up to monthly. The target here is to sort of keep the index at a reasonable amount of size. And we do this because creating an index a day makes it easier to manage the data in the cluster itself. So the best way to sort of get rid of information that's in your cluster, and especially when you're sending hot information, you really want to keep only the most current data in that cluster. The best way to do that is to delete an index. Elasticsearch does have APIs that allow you to delete individual documents, but they're not as performant as simply dropping an index. Much like a database, you drop a table. It's a quick, easy operation. So you'll have some structure like this, time-based indices, and your data will roll in and out of the cluster. So you can use query APIs to retrieve data from Elasticsearch. This is a quick example where I'm querying the verb for my Apache web log lines. The value should be get. That query will go to the query engine. It'll distribute across all of the shards that relate to that index, that are part of that index. And Elasticsearch will match the verb against the verb field of each of the documents and bring me back a set of matches across all of those documents for the ones that have the verb get. Elasticsearch being a search engine, by default, there is scoring and sorting that's applied. Now in log analytics, that's not usually useful because I'm either analyzing a big data set or I'm just pulling a whole set of results that relate to, say, some host or some verb or what have you. And so the tools that like Kibana will send a query that doesn't require scoring. But in either case, I take my match set, I score it, and those are my ranked results. Now down at the query engine level, as I said, Elasticsearch, we have the big capital I index that contains all of the data that you're sending in. For each of the fields, we have a lowercase I index that contains an index for a particular field. So for the verb field of my Apache weblog lines, I will have an index that contains every value that I've seen in that field. And for an HTTP verb, that's only going to be about 5 entries. Each of those value entries points at what's called a posting list, which is a list of all of the documents that contain that value for that field, right? So this is called a reverse index. This is a kind of core data structure for search engines. If I send in a query, for instance, host is, 10.1.68.12, and verb is get, then Elasticsearch will pull the get values from the verb index. It'll pull the host values from the host posting list from the host index, and then it'll perform a set intersection on the two of those to generate the set of matches. And this is, the reason I'm going into this is that Elasticsearch and search engines are built this way to provide this kind of very fast matching. As we look at Elasticsearch performance, the match step is typically not the long pole. It's usually the scoring and sorting, especially for search use cases. For log analytics, then, we have an additional step that Elasticsearch can perform. So in this case, again, I'm looking for a particular set of log lines, those that have the verb get, and perhaps I want to compute some statistics about either the hosts that are issuing those requests, or I want to compute some statistics about the size of data that I sent out for those requests. Elasticsearch will send that query into the query engine and generate the matches as we discussed just before. And then we'll run, it's not exactly like this in the code, but we'll run the moral equivalent of an analysis engine. And that analysis engine will go and retrieve the source document for all of the matches, and then it can compute statistics on the fields in those documents. Some of the things that Elasticsearch can do, first of all, is histogram. In a search use case, you would very commonly see this. It's called faceting. So if I search for a shirt and I want a list of brands and counts for how many of the shirts are of that brand, that would be histogramming, faceting. Similarly, if I wanted to see for the verb get the histogram of hosts that are issuing that request, Elasticsearch can look at the source documents for all the documents that match get and pull out that host field. We have some numerics, min, max, sum, average, standard deviation, a couple of other ones. For numeric fields, things like the bytes that I sent out for my GET requests, I can run those numeric calculations and come up with a number or metric for that. I can do bucketing by terms and even nested bucketing, which can be very useful. So if I want to look at the distribution of calls by region, and then by application, and then by something else, I can do that fully nested set of aggregations to get a hierarchical view of what's going on. So Kibana, again, is the real-time visualization tool that I use to examine my data in Elasticsearch. And Kibana is a thin web client. I simply use it as in my web browser. And I'm able to create visualizations like the below. These are based on CloudTrail data, and they give me the overall calls that I'm making to AWS. They tell me the regions, the services I'm calling, as well as the the ARN, the person who made that call. This can be useful. We have one use case, Expedia, spoke with us at reInvent and at some of our summits. They actually used this CloudTrail data and this kind of workload to find a billing issue that they were having where they were seeing spikes in their billing, and they were able to pinpoint the account that was making those calls, and they were able to trace it back and figure out what was going on. Onto the covers, Kibana is simply issuing Elasticsearch requests. So in this case, for all of those visualizations I had there, they come down to a request each. An example request here is to look at the event source keyword and to do a histogram across that, which is called a terms aggregation. You can see the timestamp range in there. So Kibana itself is able to narrow and widen by time. It's also able to auto refresh. So I have this real-time, near real-time view of my data, and I can expand that window out and look wider to find patterns and trends. The query goes to Elasticsearch. It's going to reference some set of indexes, usually only today's index, but for visualization, I just put 3 indexes in there. That query will then get distributed across the shards. The result will be calculated and come back out. Kibana will then turn that into, in this case, a pie chart, but there are other visualizations that Kibana can do. So I wanted to touch briefly on scale, especially when you use Kinesis Data Firehose. You want to think a little bit about scale and concurrency and figure out the sizing of the cluster that you're going to create based on sort of the data that's coming in. So the things that you control about scale, you control the instance type and instance count that you set for your Elasticsearch service domain. You set the storage. Some of our instances that we support have attached ephemeral disks, in which case the storage is set by the instance. And also we support EBS in some of our instance types where you can choose an amount of storage that you want to deploy. And the final thing is the shard count. You set the shard count either when you create the index, or if you're using Firehose, you would set what we could, a template. That's an API that you can call in Elasticsearch to set basically some defaults for any index that matches a wildcard. And the very, sort of the fundamentals of scaling. The first thing that we like to do is look at how much storage we need. Because it's concrete, it's fairly easy to predict, and it gets you most of the way to initial scale point. So I have a formula here. This formula, like all magic formulas, it will not be right for you, but we'll talk through some of the numbers in there and what they represent. So I start out with the source I need per day. So if I'm sending 500 gig of logs or sending a terabyte of logs, then I would start with that. I multiply by 1.1. When I'm sending my source log data to Elasticsearch, Elasticsearch is creating indexes. The index's size is not directly the same as my source size. The index size typically inflates. Typically, it's about 10% larger. It can be as much as 10 times as big or 1/10 the size. So a lot of this depends on your parameterization. One of the ways that you can optimize your usage is to look at your schema and adjust to store less, so your indexes get smaller. But we assume a 10% inflation. For every replica, I'm going to add another copy of the data, so I need storage for that. So I multiply by 2 because we always have one replica, again, for redundancy. 7 here represents the number of days that I'm going to retain my data in the cluster. 7 is a pretty common number. We see everything from just a few days out to a few months. Again, Elasticsearch is most commonly a hot store, so we don't usually see data staying in there for too long. In either case, whatever your retention window is going to be, you'll put your number of days in there. And then we have a 15% overhead that we use so that the disks don't fill up to the point where Elasticsearch can't use them anymore. If we apply that formula, 1 terabyte of daily source needs 17 terabytes of storage for 7 days of retention. The more complicated thing to wrestle with is the CPU and how that is distributed, or how your work is distributed across the CPUs and how many you need. The first one really goes to storage. The second one really goes to instance type and instance count. And here we have to get a little hand wavy. If we look at our indexes and how many of them are active at any given time and how many shards that represents, then we can say that certainly it's a best practice to keep the number of active shards, less than the number of CPUs that are in the cluster. So for instance, if I have 4 data streams, something like syslogs and weblogs and clickstream logs and one more, and they're generating a terabyte of source a day, but I have those 4, and for each of those 4 indexes, I have 5 primary shards and 1 replica, or in other words, another 5 shards. Then I have 20, 4 times 5 primary shards, and 20, 4 times 5 replica shards, which represents 40 shards that are active when I'm writing to the cluster. Because as I write to the cluster, I'm going to write to each of the indexes, right? So I want to have more than 40 CPUs in my cluster, and we'll pick a number, say 64. It's almost certainly wrong. That fell off the screen there, but it's almost certainly wrong. But with scaling and capacity planning, it's really important to pick a starting point, deploy, monitor, and adjust. That's always our expectation. It's not a deterministic thing where you'll get it right the first time. As I mentioned before, the concurrency really can drive a lot of need for capacity. So if I have a Firehose with 5 megabyte buffer and it has 5,000 1K records per connection, and if I set my flush rate so that I'm basically flushing that every second, then I'll basically have a connection a second. Now, if I try to send all 5,000 of those records individually from each of the hosts, right, then I'll have 5,000 connections, and the number of shards that I need and the number of CPUs that I need to process that is 5,000 times, right? So this is, again, where the collection phase of the data flow is really important. We can boil all this down into a table, again, with the caveat that this table is wrong. I can't tell you exactly, without knowing your workload and exactly how you're using it, how much you need, but this is a cut at some Tshirt sizing based on the formulas that we talked about. And if I'm looking at my data per day and the total storage needed based on the formula that I presented, and then I can go to instances. So you'll see I have 2 M4R4 large, 4 M4R4 large, 6 I3 2X large, blah, blah, blah. All of those choices are driven by the amount of storage that you can deploy for those instances. And I will say, as an asterisk, this table is built before we supported the 5 series instances. So this is it if we didn't have 5s. Now that we have 5s, things have changed a little bit. We have to come back and revisit this. But the idea here is to look at what is the maximum storage I can get per instance, divide that by how much storage I need, and then I get an instance count and an instance type. You can see the active shards column. That is derived from the number of CPUs that are in those instances that I've recommended. And so for instance, the 2 M4R4, the large instances have 2 CPUs, there are 4 CPUs total. I kind of fudged a little bit here. I feel like if you have 4 active shards, you're probably okay on those, and so on up the line. So let's turn to security. We have, again, a multi-layered security setup that you use when you use the service. At the very lowest level, we do support integration with KMS to support encryption at rest. So the data that's in your cluster and the backups that we send to S3, those are encrypted at rest. We do also support node-to-node encryption within the cluster so that your communications are encrypted when they go internally. We also support TLS to the endpoint. Then moving up the stack, we do have identity and access management. As I said, that allows you to control by principal or by IP address the actions that different sources can take on the cluster down to an index level for API. You can launch Elasticsearch service in your VPC, or you can launch it in the public. So, the endpoint that we create for you, either that will be exposed within your VPC or it'll be exposed on the public internet. If it is a public endpoint, then IAM is your main way of doing access control. Within your VPC, you can employ subnets and security groups to help you shape the traffic that's going in. As a side note, as of today when I'm speaking, Firehose does not deliver to Elasticsearch service in a VPC, so you have to create a public endpoint to use Firehose. At the top level, we have Cognito integration. This allows you to create a login experience. Actually, Cognito creates the login experience for Kibana itself, and you can hook it up to your federated identity provider. You create a user and identity pool in Cognito. Based on that, you assign IAM roles when those people log in via Kibana, and then that controls their access. At present, the access control for Cognito-based authentication is cluster level. There's a lot of other features that I am not going to cover. A lot of good, exciting stuff happening in the service, and I mentioned the 5 series launch. That's been very exciting, and I encourage you to go check out our overview page on the AWS website. So today we covered a modification of the more usual ELK stack. We talked about how to use Firehose as a delivery stream to get your logs from your data producers, how to flow those logs into Firehose so that you can do collection, buffering, how to transform with the call out to Lambda, and then how to deliver analysis and reporting with Kibana. I hope you've enjoyed. Thank you very much.